Thanks, thanks you guys for showing up this morning. These days, I think a lot about actions with groups on triangulated categories, CP categories. In particular, groups like braid groups. It's relevant for categorification because one of the great things that categorification produces is a large stock of examples, triangulated categories with actions with braid groups. And these actions are extremely rich and not that well studied. And one feature of their richness is that if you have a group acting on a triangulated category, then often you can build from it the action of the same group on some spaces, some complex manifolds, some simplicial complexes. There's really a whole zoo of spaces. So if your input is a group acting on a triangulated category, which is kind of part of linear mathematics, then the output is some sort of continuous mathematics, action of the group by homeomorphisms on some spaces. So I think these things are interesting to study. And one of the prominent words that comes up when you start thinking about these things is the moduli space with Bridgeland stability conditions. So that's a complex manifold that's associated with triangulated category. And the groups the braid groups act on stability spaces. If you want to study those actions, one of the first questions you would ask is, well, what's the topology of the space of stability conditions? What is this space with which is being acted? And that's kind of really the kind of question that I'm thinking of. Try to understand the topology of the space of stability conditions and maybe some other spaces on which the braid group acts. So I'm probably not going to say a lot about that here, but that's maybe an important thing to keep in the back of one's mind. What I'm going to try to do is tell you some combinatorics of root systems that emerges when you start thinking about the topology of that space and state some conjectures. So I think basically, you can call me on this if you're skeptical, but I think basically all the conjectures I'm going to state are theorems in type A and open outside of type A. Okay, and some of those theorems are due to Anand, Asilata, and I, and some of those theorems predate us. Okay, all right. So let's start. So in this talk, kind of for some combination of simplicity and laziness, I'm just going to think about ADE, though everything I'm saying can be formulated more generally in the generality of arbitrary Coxeter groups. But I'm going to think about ADE. Okay, so let's let lambda be the root lattice. So if my Lincoln diagram has n nodes, then the root lattice has a basis given by n simple roots. And the pairing on the lattice is determined by the pairing on the simple roots, and that's, a root pair with itself is a simple root pair with itself is 2. If the corresponding nodes in the Lincoln diagram are connected by an edge, then the pairing is -1, and if the corresponding nodes are distinct and not connected by an edge, then the roots are orthogonal. So that's the root lattice. Okay. Okay, so now once we have the root lattice, let's define a central charge. So I'm taking this terminology from the theory of stability conditions. A central charge of the root lattice is central charge on Z is just a linear map, so homomorphism of the union groups from the root lattice to the complex lattice. So what you should think is that you have shoved the root lattice into the complex plane. Okay, so that's what a central charge is. Actually, I want one condition on my central charges, such that there's a condition that we call the central charge unique, which is that if I evaluate the central charge on a root, so let me say that capital P denotes the roots of my root lattice, then the central charge does not vanish on any root. Okay. So if you look at all linear maps from, if this is rank n, if you look at all linear maps from here to here, that's a complex vector space of dimension n. And here we've just removed some complexified vector planes. Okay. So this space of central charges is a complexified vector. Okay. All right. Okay, so let me just introduce a couple other words. So So let's fix a central charge Z. A framework, we really actually call it a Z framework. But the framework, I'll say the framework, but the framework is, it's just a subset of roots. And really, and maybe it's better to think instead of some abstract subset of roots, I mean, really to think of their, the framework is really their complex numbers you associate within the central charge. So I've drawn a couple pictures of central charges here. So here, this is the central charge of the A3 root systems. The A3 root system has simple roots alpha 1, alpha 2, alpha 3. I've shoved those anywhere in the complex plane I like, and then that determines a linear map from the root lattice to the complex numbers. And the other roots, I've just drawn the positive roots here, but the other roots go where they go. And so a framework for this central charge would just be, take a subset of these vectors. Here's a different central charge. It looks similar. The difference is that I've swapped where I sent alpha 1 and alpha 2. But it doesn't look very different at the moment. So a framework is just a subset. So, okay. So, do you have any upper plane restrictions? No. I drew the positive roots in the upper half plane here, but that was just for convenience, not important. Okay. So an infinitesimal, so definition. So if I have another linear map,
you require F2, sorry.
No. But if you like, you can take, you can just think about a subset of positive roots, but no. It could be any subset. Okay. Yeah, the theory won't change if I. Okay, so if I have another linear map to the complex numbers, so think of this as a vector in the tangent space at Z. So then this tangent vector is called an infinitesimal motion of a framework F at Z if okay, so think here I've got you're at some central charge, look at the tangent space, take a tangent vector, and just ask yourself, what is it doing to the length of the vector Z alpha? Okay, this condition is the differential of saying that the length remains constant. So think in your head, you're moving in a path in the space of central charges, and you're asking what happens to the lengths of the vectors in your framework. So a tangent vector will satisfy this if all the vectors in my framework, if their lengths stay constant as they move along the path. That's all this is saying. Yes?
I have a dumb question. Is there a reason you didn't draw alpha 1 plus alpha 3? I forget the definition.
It's not a root of A3.
Yeah, okay.
I'm only drawing the roots. Okay, so that's an infinitesimal motion, and one more definition. So a framework F is isostatic. All this terminology is stolen from robotics, and it's all kind of subject to complaint or change. But a framework F is isostatic if the only infinitesimal motions of it are trivial. Meaning, there's always one kind of infinitesimal motion you can do, which is the differential of a rotation. If I just rotate the picture, no, the lengths of these vectors won't change at all. So a framework is isostatic if all infinitesimal motions of F satisfy, say, all infinitesimal motions of W, F satisfy alpha equals 0, not just for all the alpha in the framework, but for all roots. So that condition is basically saying that you're the rotation. Yes.
Isn't your isostatic at C?
Yeah. Okay. A framework is, I've always had to fix a Z to be able to talk about it. Okay. All right, so now here's a, so now again, fix that. Here's a question. Which frameworks, which subsets, say other groups are minimal isostatic? Meaning they're isostatic, so the only way if you want to move the central charge and preserve the lengths of the vectors in your framework, you got to rotate the entire central charge. Minimal just means, and if you remove any root from the framework, that will no longer be the case. So if you remove the root, you'll pick up an interesting motion. So these frameworks that don't have interesting motion, but if you remove any root, they have an interesting motion. So it's a question. Okay, so.
Tony, can you give an example of a framework that's non-isostatic?
Yes, sure. Just take alpha 1 by itself. Okay? Then what I can do is I can move alpha 1 preserving its length, and move alpha 2 and alpha 3 freely in some other way, which changes their lengths. Since I have free choice, that determines the central charge. Once I said what happens to these guys, it determines the central charge. And it's not a global rotation because some lengths change. Yes. Okay, I'll draw some pictures in a moment of some of these things. So, okay, so if you have a minimal isostatic framework and you remove an element from it, then you have a non-trivial motion after you've removed an element. So actually let me give you one more definition. I realize this is a lot of definitions, but hopefully there will be a payoff. So one more definition. Good. W is, so let's let W be an infinitesimal. So let W be an infinitesimal motion of a framework F. So that means that these vectors are orthogonal to Z at Z. So that, let's remind you, that means that these guys are orthogonal all elements of the framework, but not necessarily for all roots, just for all the elements of my framework. Okay, so W is called expansive if for other roots you don't necessarily have 0, but you always have something non-negative. Okay? So if you have a motion, you can ask whether or not it's expansive. Now, another question you can ask is if F is obtained from a minimal isostatic framework by removing one root, well, then then linear algebra tells you it picks up a non-trivial motion. And you can ask, does it pick up an expansive motion? Is the root one root alpha? Is the resulting non-trivial motion of F minus alpha expansive? Well, it's actually a line of motions, and in one direction it might be expansive, in the other direction. You get it? Okay. The possible state of motion being one-dimensional. Yeah, if you take, yes, like this positive, if you have a minimal isostatic guy, the space modulo rigid motions, the spatial motions is 0, the linear algebra tells you remove one guy, it picks up. Okay. Okay, so then can ask a combinatorial question, which is which, so again, we fix Z at Z, which frameworks here as expanded. I'll just say which frameworks are expanded. Meaning they're a minimal isostatic framework without a root, and the resulting motion is expansive.
Every alpha?
Again?
The rule every alpha?
No, I mean the which frameworks F minus alpha. This is the framework I'm calling expansive. Okay. Okay, so this is a question you can ask. What I want to keep in mind is this is not a question about roots in the abstract root system. This is a question about a particular embedding of those roots into the complex plane. So the answer to this question is heavily dependent on Z. Okay. Yes?
If you have a non-trivial motion, it's one of these linear maps. Isn't the negative of it also a non-trivial?
Yes, but what I mean in this kind of motion, it or its negative is expansive. The feature you might have is that no matter which way you move in this one directional motion, some roots get bigger and some roots get smaller. That would not be expansive. Okay. So this, the first thing I want to say is that the answer to this question is combinatorially interesting. Okay. So I'll make a conjecture and then I'll draw the situation in type A. Okay. So again, I just want to emphasize we have fixed our central charge Z. So this definition depends on which guy we choose. So define a simplicial complex whose vertices are the positive roots and whose simplices are you put a bunch of positive roots together into a simplex if that set of roots is expansive. Okay. So subset of roots is expansive. I'm sorry, is a simplex if it is expansive. I'm not going to write out exactly what that means. Just keep in mind it means this. It means if you get a minimalized typic guy and you remove the root, that it has an expansive motion and it continues. So this is a simplicial complex, which I'm sort of saying quickly, and then here's the conjecture.
I'm confused. I mean, these
Yeah.
are top-dimensional simplices.
The top dimensional simplices would be the things of this form, but any subset of something of that form is the lower dimensions.
Okay, but a subset of expansion
Yeah.
possibly be.
Yes, definitely.
So can I ask, do you have to choose the root that is to be deleted to get an expansive thing? Or
If I take a minimalized static framework,
yes,
when I remove a root, the resulting framework might be expansive or it might not. That subset defines a simplex if the resulting thing is an expansive motion. If it doesn't, it stops.
so the thing that's expansive is the rigid guy, the minimalized static guy minus.
Yes.
Okay.
Yeah, that's right.
Okay.
So conjecture is if the rank of the root lattice is n, then this simplicial complex, maybe I'll call it X gamma, is a sphere. And the sphere depends on the rank. So that's something about saying this subset of expansive guys is extremely industry. So the picture you should have in your head is we have this space of central charges. It's a complexified hyperplane complement. Over each point is a sphere. But the simplicial decomposition of that sphere depends heavily on which central charge we're at. So over some central charges, it'll have some simplices. If you move the central charge, then the simplicial decomposition of the sphere changes drastically, but it's still the same sphere. Okay, that's the conjecture, the combinatorial conjecture, and I just want to explain. So I just want to draw a couple pictures in type A and to illustrate it before I move on to the. Okay. Yes.
And this is for any bridges, or any central charges.
Yes. For any central charge. This should be true. I mean, the precise simplicial complex looks very different. I mean, so for example, in type A, you can rephrase all of this in terms of graph theory. And that's both what makes it theorem in type A and also makes it understandable. So a central charge in type A is the same thing as a configuration of points in the plane. How? Let's just plot the origin, alpha 1 plus alpha 2, alpha 1 plus alpha 2 plus alpha 3, alpha 1 plus alpha 2 plus alpha 3 plus alpha 4. Just look at those, plot those points. That's a configuration of points in the plane. And if you just draw those points, then the values of the central charge at other vectors are just translates of the straight line segments in that picture. Okay. So in other words, a central charge in type A is just a kind of immersion of the complete graph, straight line immersion of the complete graph. So in this one, note that there's a big difference when you draw this picture between this. So I'll do the same thing here. So these are different central charges, and these are two very different planar embeddings of the complete graph on 4 vertices. They have completely different convexity. So the combinatorics of this simplicial complex is governed by the convexity of this picture. In particular, I don't want to go on this too much. So in the language of graphs, here I've drawn the maximal simplices of my, in this case, it's rank 3, so I'm building a 3-sphere. This central, in this central charge, the maximal simplices of that 3-sphere, there are 8 of them. I've drawn them here. These are the 2 minimal isostatic frameworks. And these are the expansive guys. And here, in this picture, there are 3 minimal isostatic frameworks, and there are 9 maximal simplices. So here, this is a 3-sphere for the maximal simplices. There are 8 of them, and here there are 9 of them. So the combinatorics is kind of interesting. Okay.
How do you know which of the subgraphs are isostatic?
So, okay. That question in type A was completely answered about 20 years ago in the theoretical computer science community. So they study planar embeddings of graphs. This is important in robotics because if you're trying to program some robot arms to move along rigid rods, you want things like you want to make sure that the arms don't collide with each other and all sorts of stuff. So you want to embed a graph in the plane and move it rigidly so that you don't have collisions and things like that. So this sort of mathematics shows up. In some sense, all I've really done here is note that graph theory is the type A root lattice, and the definitions make sense for other root lattices. And so then you get conjectures, but.
I think we're just asking, is there any way to look at those subsets and just see like, oh,
yeah. Yeah. So it's easiest to say if the endpoints, if their convex hull is an engon, and then the answer is the maximal simplices are exactly a triangulation with an external edge loop. So the isostatic frameworks are exactly the triangulations, and you get to take a triangulation and remove any of the convex hull edges. Here, the answer is a little bit different. You have to replace the word triangulation by the phrase pointed pseudo-triangulation. which is kind of a topic for another talk. But yeah, there's a complete answer to that question. And the reason this is a conjecture is because I don't know what the type B analog of that is yet. Okay. Okay, so that's the combinatorics. That the upshot, the sort of takeaway from the upshot is that an interesting question for me. Which frameworks are expansive? It's a kind of interesting part of root combinatorics. It's heavily dependent on how you embed the roots. Okay, so
Are there any conditional that the generic rules?
say again,
That being generic, but I'm gonna throw everything over the line.
you can. The definitions get a little bit. The answers get a little bit more complicated. But yeah, actually, interestingly, the computer science community only considers a case where the points are in general position, but you can extend everything to a single number. Yeah, on a wall, so to speak. And this conjecture is supposed to be general. Okay. Okay, so now
The conjecture is proven in type A? Is that what
yes, I mean that's just importing existing theorems in the language of graphs and rephrasing them in terms of okay, so homological algebra. So associated to the Dinkin diagram, there's a triangulated category. This is the two-combinatorial category of gamma, which I'm not going to completely define for you, but many of you have seen it in some guys. If you like, it's the homological category projective modules over the zigzag algebra, the graded projective modules over the zigzag algebra, or you can phrase it in terms of the pre-projective algebra. But what do I want to say about it? So it's generated by, in the same way that the root lattice is spanned by n simple roots, this category is generated by n objects, and in the same way that the root lattice is determined by the pairing of the simple roots, this category is essentially determined by the Hom spaces between these generators. And what are the Hom spaces between these generators? The Hom from Pi to a shift of Pj. So this is a triangulated category, so it's suspension. This is like this lattice. So it's let's say my Hom spaces are K vector spaces, and this is K, S 0 or 2. Is K. If I and J are connected in the Dinkin diagram, then there's a one-dimensional Hom space, which would be 1, and it's 0 elements. So if you look at Hom from Pi to a shift of itself, that's two-dimensional. So in particular, so if you look at all Homs of any degree from Pi to itself, that's isomorphic to homology of the two-sphere. And that's why we call these guys spherical objects, because their endomorphism algebra is the homology of the two-sphere. So, in fact, more generally, if you have an object of this category and its endomorphism algebra is homology of two-sphere, so we say that Y is spherical. And these spherical objects of this category are very important and will play a role in what comes. Okay. The one thing we're interested in studying this category is understanding the spherical objects. Another thing we're interested in understanding that I need to spend a few minutes saying something about is the moduli space of stability conditions. So this is my triangulated category. And associated to this triangulated category is a complex manifold called the moduli space of stability conditions. So this is a complex manifold. I want to tell you some features it has. I'm not going to completely define it for you, but this definition is due to Bridgeland. I just want to give it a So one thing that's nice about this category is that it has a braid group action on it by autoequivalences. And this construction is functorial for autoequivalences. So that induces a braid group action on this space by homeomorphisms. And one thing that I'm not going to elaborate on much here, but that I do want to advertise is if you fix a braid and think about the space of stability conditions with the action of that particular homeomorphism, that's a dynamical system. And it's an extremely interesting dynamical system. And, you know, in if we've been talking yesterday in the panel about things that we are currently thinking about, then I would have said this categorical dynamics is an extremely interesting part of model representation theory. So it's sort of think about a braid acting on this space. If you want to do anything with that, it might be nice to understand the topology of this space. Conjecturally, this space is contractible. Trying to understand that and prove it in the examples we care about is kind of what's motivating a lot of this combinatorial. Okay. Okay, so stability conditions. What is so remarks about stability conditions. What do I need to know about stability conditions? Well, first of all, the definition of stability condition is a pair. So P is a collection of subcategories. They're typically indexed by the real numbers. And Z is essential charge. From the Grothendieck group, which in this case is the root lattice, to the complex numbers. So that's the kind of obvious connection between stability conditions on this triangulated category and essential charges is that essential charge is one of the two pieces of data in a stability condition. The definition of a stability condition also has a compatibility with between these two. So these two together are supposed to satisfy some axioms. And the important things so if we fix a stability condition, then what do we get out of it? Well, one thing we get is that every object in the category gets expressed as an iterated mapping cone of objects in these subcategories. So these subcategories, the objects of these subcategories are called semi-stable objects. They're not the whole category, they're just a small piece of it. But if you fix a stability condition, then one of the outputs that comes from the compatibility here is that every object in the category gets a distinguished expression as an iterated mapping cone of these guys. So that writing is, as a name, is called the Harder-Narrowson infiltration of Y. So, you fix a stability condition, every object in the category gets a Harder-Narrowson filtration. Yeah? Have different stability conditions, and the objects in question will have different filtration. Two, and so the classes in the growth entity group of the semi-stable guys, of the indecomposable semi-stable guys, are exactly the roots. So what you should think, this is a big black box, but you should think, if you fix a stability condition, every object in the category gets expressed as a sum of roots. I mean, literally, it gets expressed as the iterative mapping component of semi-stable objects, but each semi-stable object corresponds to a root. Yes?
In unacountable order. Like, is that correspondence sort of?
So if this stability condition is generic for these two Flavian categories, if the stability condition is generic, then there is a bijection between positive roots and semi-stable objects off the ship.
But like a canonical bijection, or you choose?
Yes.
Okay. Yeah. And then are these categories these of the triangulated categories? They're okay, but they're not like those are shifts, right?
No.
Okay.
The shift, if I take P sub P and I shift all the objects by one, that's actually the category P sub P plus one. Okay. Yeah. Okay. And three, just as a bit of a remark, one other thing stability condition gives you is it gives you a way to assign to every object in the category a non-negative real number called its mass. So each stability condition gives you a way to assign a mass to each object, and that's an example of a metric in the sense that Rekia talked about in her talk. It's a non-negative number associated to each object in the category, and if three objects stick to an exact triangle, then those numbers satisfy a triangle equality. The metrics that she referenced were non-Archimedean. These are very different. These are kind of more model of a I haven't told you the definition, but they're modeled on the geometry of the plane. But so maybe you don't care what a stability condition is, but if there's one sentence to take away, it's a moduli space of metrics on the triangulated category. And a triangulated category has potentially lots of kinds of metrics on it. This is one kind. Okay. All right, now, so for these categories, so what's the kind of the conjecture here about the topology of these categories? Well, so a point in here that was a pair, a bunch of subcategories called slicing, and a central charge. So if you have a stability condition, you can forget this P and just remember the central charge. So for these categories, that forgetful map is a covering. And so there's a conjecture, which is that this conjecture makes sense for arbitrary concatenated groups. So the conjecture is that actually this space is the universal cover. And moreover, that universal cover is contractible. So the conjecture is that these guys have boring topology. So actually in the ADE type that I set up earlier, this is known. It's open more generally. And for me, it is the most important open problem about braid groups associated to construct. Most things we don't know about braid groups associated to arbitrary construct groups would be known if we could prove this state. Yes. Say again?
Is the braid group acted
Yes, exactly. That's exactly right. The braid group action there are two braid group actions in the picture, as you just pointed out. One is pi1 of the central charge space is known to be the braid group. On the other hand, the braid group inherits an action on here by this. That action is by deck transformation.
And what's T gamma of that simply laced?
Excellent question. When T gamma is not simply laced, you need to work with triangulated categories endowed with an action of a fusion category. Exactly in the setup that Ed talked about. Indeed, like our initial talks about this fusion categories and everything else was exactly to try to make sense of this. You might also think the Hecke category, which exists for arbitrary Coxeter groups, should play some role here. It does. The kind of things to keep in mind is you need to think about the Hecke category, but you also need to think about the categorified J ring of Lustig. That world together should give rise to this in arbitrary. Yeah, excellent. Okay. All right, so every object, so if you fix a stability condition, every object in the categories gets written as an iterative mapping going to semi-stable objects, and the semi-stable objects correspond to the roots. So a question you can ask so fix a stability condition and let's also fix Y a spherical object. Not just any old object in T, but a spherical object. So an object whose endomorphism algebra is as small as possible in this category. It's just two-dimensional. So the question you can ask, so that you can consider the partner-RSM infiltration of Y. I haven't explained how it's constructed, but just black box, the fact that a stability condition gives you one. Now, the things showing up in the Harder-Narsum infiltration all correspond to roots, right? So you can look at this, think about the roots that show up there in the central charge Z. That's a framework. So this is a Z framework. And so you can ask, if you take spherical objects in the category, which frameworks appear? So that's the question. So the question is, if Y is spherical, which frameworks appear as tau of Y? Okay. The conjecture is that it's exactly the expansive frameworks from earlier. The conjecture is that the Harder-Narsum infiltrations of spherical objects are expansive frameworks. Okay, so I have not really explained enough or clearly enough to I think to really say much about what this means or why it's important. But I'm very proud of this conjecture. To me, it's I mean maybe it's false, but it connects two things that at least to me seem to have no right to be related to one another. One is something which is very deeply part of homological algebra associated to quivers. And the other is something which is really about the planar geometry of root systems. And I've wondered for years what constraint, like if you just think about arbitrary objects in a category, anything can show up in its Harder-Narsum infiltration. But for OL and I years ago were kind of thinking a lot about how to describe constraints on the Harder-Narsum infiltration of spherical objects. And this is, I think, the answer. It connects the kind of planar rigidity of root lattices to properties of the filtration. So I think it's interesting. So I only have 5 minutes left. So first of all, this is maybe a couple words. So first of all, this is a theorem in type A. This is a theorem in type A. So and I'll just maybe say out loud why it's a theorem in type A. It's a theorem in type A because in type A, central charges can be thought of as configuration of points. So if we want to make use of that, then we have to think about spherical objects somehow in terms of configuration of points. And Kovanov-Seidel told us how to do that. So Kovanov-Seidel in type A say that there's a bijection between spherical objects and curves joining the punctures. So if you want to prove this conjecture, the first thing you do is you kind of soup up Kovanov-Seidel a little bit to understand this framework in terms of the curve. And the short version of that is that this is a curve, and this is a framework. This framework is exactly the HN support of this curve. Like morally, the tie between this guy and frameworks in type A is pull the Kovanov-Seidel curve time. And that allows you to, that fact that this is a curve and you can think about the curve allows you to connect the story in type A to these kind of graphs, and that's what allows this one to prove this. The second thing is just say, this is the kind of,
There's some understanding of the collection of spherical objects.
say again?
Is there some understanding of the collection of spherical objects with the same framework?
Sort of. Let me ask me that again later. So here's a kind of I'll put theorem in quotes. And then say why. Theorem in quotes is that the conjecture implies the contractibility. Which is to say that Anand, Asilata, and I gave a new proof of the contractibility in type A that was already known in a kind of roundabout way. And so we wanted to prove that this space was contractible, and so we needed to contract it. So we needed to define a vector field, which gave a contracting flow. And the way we defined that vector field was using expansive frameworks. And this is the kind of key thing. So basically, in any category where you can prove this theorem, I can tell you a vector field, and then we can prove that it's integrates to a contracting flow. Yeah, anyway, so that's maybe a topic for another thing, but this is just to say why I am interested in this conjecture, because this is a problem that's easy to motivate. This conjecture is difficult to state, much less motivate. But this is true. There are this theorem is in quotes because there's quite a lot that goes into this arrow. I mean, once you prove this, I have to use it to define a vector field. You can do that. If you try to then something fascinating happens. So when you define a vector field on this space, which you try to integrate to a contracting flow, this conjecture allows you to define a vector field. That vector field turns out to not be continuous. It's piecewise differentiable, but it's not continuous. Which means when you integrate it, you're trying to solve a differential equation whose right-hand side is not continuous. Now, you're not trying to differentiate such a thing, you're trying to integrate it. So, and indeed, there's this textbook from the late 1980s, I think, by Filipov, which is called Differential Equations with Discontinuous Right-Hand Sides. So this is an example, and applied mathematics has developed a lot of tools for dealing with things that are now called Filipov vector fields. I remember when we discovered that our vector field was not continuous, I was really, really disheartened. And Anand Deopurkar, one of my collaborators, said, well, why are you worried about that? They were integrating it. And sure enough, he's right. So this natural vector field, so this category, and indeed many others, have natural piecewise differentiable but not continuous vector fields on them. Those things are ubiquitous in the subjects. And they're all wonderful examples of this kind of piece of differential equations, which is well developed in applied mathematics and was previously unknown to me, and I imagine unknown to many of you. So one kind of moral takeaway here is that this theory of the Lie law of vector fields is also something that just arises naturally if you think about homological algebra. And I expect that there will be more appearances of this in related situations in the future. But that theory is the kind of big piece of input into this era, this theory of differential equations with discontinuous right answer. Okay, we'll stop there.